Well, now we're going to start trying to use these equations. And as I said, we can't solve them in their most general form with paper and pencil ever. But a lot of flows that we're going to look at don't involve the entire equation. There are different flow regimes where certain terms become important, other terms become negligible, and we can definitely make progress on various flows by identifying those situations. So we're going to start taking a look again at the x momentum equation here. Rho, times this quantity here, du dt plus u du dx plus v du dy plus w du dz equals minus dp dx plus mu del squared u. So that's all these second derivatives. So this set of terms here, these u du dx, v du dy, w du z, those are considered the inertial terms. So those are essentially forces that occur because fast-moving fluid is either entering or leaving our space, and therefore pushing the fluid around, either slowing it up or speeding it down as it enters and leaves. And this is the same kind of thing that causes a hose to sort of push back at you when fluid leaves the hose nozzle. So that's the kind of force that is. And then you have pressure forces. Of course, you know what those are. We've studied those in hydrostatics. And then you have the viscous forces. And we certainly are getting increasingly familiar with those. These forces that come from the fact that fluids, slide relative to each other. And as they slide, some fluids, are stickier than others and therefore drag on each other more than others. So when you go to steady flow, which is the only situations we're really be able to solve with paper and pencil, the UDT goes to 0, as you well know from many classes. And so that leads to, just these terms here. Now I've divided everything by density. So I have 1 over rho times dp dx. And then instead of mu, I have nu here. So the kinematic viscosity instead of the dynamic viscosity. And that's typically the form that people work with when they're dealing with these flows. So many steady flows involve a balance between two of the feed forces. Not always, but many. So many steady flows involve a balance between two of the three types of forces. So that means one of the types is not significant or is negligible in the problem. In some cases, it is truly 0. So that's what we're going to try to do, is figure out some of those flow situations where we don't have all three. We don't have inertia, pressure, and viscosity all acting at the same time, which makes for a very complicated situation. We might just have 2 of the 3. So one of the ones where we can make really good progress on it, and we will solve this in detail later, but right now we'll just identify this as an example of what I just said, an example where you really only have 2 types of flows going on at once, 2 types of forces acting on the fluid, not all 3, is pipe flow. So we're going to take a look at steady pipe flow, and we'll come back to this and solve it. But right now my point isn't to solve it, my point is just to look at it and understand which things are going to happen in here. So if the x direction is this way and we have steady pipe flow, after a while, as the flow is in the pipe for a while, it becomes what's called fully developed. So flow develops. And so the flow might enter with a uniform velocity or something like that, but eventually the viscous effects start to creep into the flow, and the flow will take on a parabolic profile, which we've talked about in other contexts. So at some point, there will be 0 velocity at the walls because of the no-slip condition. And so the velocity profile for the fluid will take on this curved shape where it's 0 at the walls and high speed in the middle. And after some period, that shape won't change anymore. So the flow, whether at this point the velocities are all the same as those at this point and all those at this point. So the velocity stops changing in the x direction. In addition, as you can see, since the velocity is not changing in the x direction, there's no velocity in y or v either. So there's v goes to 0, w goes to 0. So you have no velocity in w in the z or the y directions, and there's no change in velocity in the x direction because nothing's changing in x. So du dx goes to 0 as well because there's no change in x anymore. So with those simplifications, let's go back and look at our x momentum equation. So we have u du dx plus v du dy plus w du dz equals minus 1 over rho dp dx plus nu del squared u. Well, we just said that v was 0, so that kills that term. We said w is 0, so that kills that term. And we have du dx is equal 0, so that kills that term. So those three terms all are gone. And so this ends up being a very simple looking equation. Just dp dx is equal to nu del squared u. Now you may not remember what del squared is, but del squared is just those three derivatives. So I'll write that out one more time for you as well here. So dp dx is equal to nu times these three second derivatives, d squared dx squared, d squared u dy squared, and d squared u dz squared. So that's your, that would be your equation in x, y, z coordinates. Obviously, when we actually get to the flow, we're gonna see that it's we'll do it in cylindrical coordinates. But at any rate, right now, what we're saying is this is an example where you have no inertial forces. Inertia is not relevant. You have pressure forces exactly balancing viscous forces. So it's pressure and viscosity, and nothing else. And so those two forces, you just have the pressure, which is driving flow down the pipe, and viscous effects because of the no-slip condition. Pushing that fluid down the pipe is going to have resistance because the resistance at the wall causes the no-slip condition, which then drags the fluid slower as it tries to move by.